Imagine waking up one day and boom, humanity's basically built a starter civilization on Mars. Not with astronauts waving flags, though, but with like 10,000 advanced robots already there, setting up shop.
It sounds like pure sci-fi, doesn't it?
Totally. But it's the ambitious scenario we're diving into today, based on this, well, fascinating stack of info you shared.
It really pushes the envelope, you know? Thinking beyond just single missions to, well, a potentially self-sustaining robotic presence out there.
Exactly. So for this deep dive, we're going to unpack the sheer scale of landing 10 starships on Mars, each one carrying 1,000 humanoid robots. We'll explore how you'd even deploy this massive workforce, the huge challenges they'd face, and just the incredible engineering and coordination needed.
Right.
And for you listening in, someone who wants to really get a handle on complex stuff quickly without getting, totally bogged down, we're aiming for those aha moments exploring this.
Yeah, our goal is really to pull out the core ideas of this plan, highlight the crucial steps, and what it all means for expanding beyond Earth, giving you a clear picture of the whole thing.
So our mission today, extract the key insights, figure out the most critical steps to get this robotic foothold on Mars, and what it really signifies for space exploration. Okay, let's get into it, starting with just getting everything there. 10 starships.
Yeah.
Landing. That's not just a step up. That's a whole different league, isn't it?
Oh, absolutely. The scale of that landing event, it's genuinely hard to overstate. Each starship, they're talking maybe 100 metric tons of payload capacity.
100 tons each.
Yeah, multiply by 10, you're potentially looking at like 1,000 metric tons landed. I mean, think about Curiosity. Great rover, right? About 1 ton.
Right.
Even the old Viking landers back in the 70s, they were under 600 kilos. This is just... yeah, a whole new ball game.
So the entry, descent, and landing the EDL, that has to be absolutely nailed.
Yeah.
Not just once, but 10 times. What are the big advances that make landing something that massive even, well, thinkable?
Well, to pull that off, you need huge steps forward in several key EDL areas. You've got to manage the intense heat during atmospheric entry. We're talking really extreme aerothermal loads.
Okay.
Then there's that tricky bit, transitioning from hypersonic speeds down to subsonic, needing incredibly precise control.
Right.
And finally, sticking the landing, a soft touchdown for such a huge vehicle. It demands, big innovations, reusable heat shields that can take multiple entries, much smarter supersonic retropropulsion for slowing down in that thin air.
Yeah, you can't just pop a parachute on a starship.
Exactly. And highly autonomous hazard avoidance, systems that can see dangers, rocks, slopes, and react instantly. It's not just tweaking old methods, it's revolutionary, really, for getting big stuff down safely.
Okay, here's where it gets really wild for me. You can't just point 10 huge landers at any random spot on Mars, can you? Where do you even aim them?
Yeah, good point. Landing site selection would be super strategic. You need safe, flat-ish areas, obviously, but also close to key resources. Subsurface water ice, that's probably top of the list.
Makes sense. Water's critical.
And think about it. 10 massive landers coming down, potentially quite close together to form a hub. You absolutely need a sophisticated orbital and atmospheric traffic management system.
Like Martian air traffic control.
Pretty much. Probably AI-driven, given the comms delay. Something orchestrating those descents, making sure they don't bump into each other, handling the communication blackouts during EDL, maybe even accounting for, atmospheric disturbances from the ship that landed just ahead of it.
Wow, that's complex.
It's an absolutely unprecedented level of coordination.
And the payoff is immediate, right? 10 starships sitting there aren't just scrap metal, they're instant infrastructure.
Precisely. They become the foundation, they've got power systems on board, workshop spaces, maybe even tools, materials. It's a huge head start compared to landing one small rover.
Okay, starships down. Safe. Now the main event. 10,000 advanced humanoid robots rolling out onto Mars. How does it work? I mean, you can't just, kick them out the door.
No, definitely not. Deploying that many robots would be this incredibly carefully planned sequence. We'd need really efficient, probably redundant ways to get them out.
Like what? Ramps? Elevators?
Could be. Advanced ramps deploying quickly. Maybe heavy-duty elevator systems moving several bots at once, or even crane-like things lowering them down gently. Speed and reliability are absolutely key.
And these aren't just, basic bots. We're talking cutting-edge humanoids, right?
Yeah.
Like the ones making headlines now. Atlas, Optimus.
Yes, the whole concept relies on robots with capabilities similar to, or maybe even better than, those top prototypes. So think highly adaptable mobility for Martian terrain.
Which is rough.
Exactly. Super dexterous hands for manipulation, and crucially, a lot of autonomous decision-making powered by pretty sophisticated AI.
A ready-made skilled workforce was the first thing they do. Step out and take a selfie.
Huh, maybe a quick system check first. Initial teams would probably deploy first, their job. Secure the perimeter around the lander, check the ship for damage after landing, maybe establish safe paths for the others.
Yeah.
This would all be heavily based on pre-mission plans and simulations, maybe guided by an AI command system on the starship, or perhaps even specific leader robots.
Like a well-rehearsed robotic ballet. And once they're out, they need to check if they're okay.
Absolutely. Job one for each robot is a full self-diagnostic. Check locomotion, arms, sensors, power, communications, everything. Then, very quickly, they need to link up, talk to the starship, talk to nearby robots, send status reports, get initial local instructions. Forming those little local networks right away is vital for doing anything coordinated.
Makes sense. Local comms first. But Mars is, millions of miles away. How do you manage the big picture? Talking to Earth, coordinating between all these different landing sites.
That's a huge challenge. The communication delay anywhere from 4 to 24 minutes one way.
Yeah, that kills real-time control.
Completely. Forget joysticking them from Houston. It forces you towards extremely high levels of autonomy on board the robots and needing a really robust local communication network on Mars.
So we can't just, have a quick video call with Robot 734 to ask what it's doing. They need the smarts to act alone.
Exactly. The current Mars Relay Network, the orbiters we use now, it's great, but it would be totally overwhelmed by the data from 10,000 robots.
Right. Too much traffic.
So the starships themselves, with their big antennas, they'd likely be the main communication hubs, maybe relaying data up to an upgraded orbital network, more satellites needed there.
Okay, starships talk to orbit, orbit talks to Earth. But what about the bots on the ground, maybe spread out between the landing sites? How do they talk to each other?
Building a high-bandwidth, tough local network connecting all 10 sites and the robots moving around is priority number one. A Martian internet, basically.
A Mars Fi network.
Yeah. It could use a mix of tech, strong radio links, maybe wireless mesh networks where robots act as nodes, bouncing signals along.
Oh, cool.
Even free space optical links between the landers for really high data rates. People are even looking at adapting 4G or 5G for space. Robots would be deploying and maintaining these relays themselves.
Wow. And with all those robots sending data cameras, sensors, the amount of information must be astronomical.
Oh, totally. Each robot is a fire hose of data. Trying to send all that raw stuff back to Earth, forget it. Just not feasible.
So what's the workaround?
Edge computing. Distributed edge computing. A lot of the data processing and initial analysis has to happen right there on Mars.
On the robots themselves?
Yes.
Or the starships?
Both, probably. Processing power spread between the landers and the more advanced robots. They'd filter the data, group it, prioritize it, send back summaries, important findings, alerts if something weird happens. The humanoids aren't just workers. They're like intelligent filters in this huge network.
Okay, so they're connected, they're processing info, but keeping 10,000 advanced machines running? That takes a ton of power, right?
Yeah.
How do you keep the lights on, robotically speaking, on Mars?
Yeah, the power demand is colossal,
Yeah.
and you need it to be reliable. Even the best humanoid bots on Earth chew through batteries pretty fast.
And Mars isn't exactly ideal for power generation, is it?
No, it throws some real curveballs. You get way less sunlight than Earth, for starters.
Yeah.
And then there are those infamous dust storms.
Right, those planet-wide dust storms that just choke everything. Didn't they cause problems for missions like InSight?
They absolutely did.
Uh-huh.
A major factor in InSight ending its mission, dust coat solar panels slashes their efficiency. So while solar is the logical long-term plan using Martian resources to build panels, eventually the initial power setup has to be really tough against dust and handle the lower sunlight.
So what's the plan? Bigger panels?
Yeah.
Robot window washers?
Both, potentially. A key early job for the robots would be rolling out huge solar farms, much bigger than we've sent before. And yeah, integrating advanced dust mitigation. That could be things like electrodynamic shields using electric fields to zap dust off.
Cool.
Special coatings that dust doesn't stick to as easily, or yes, robotic cleaning systems, maybe even systems that use vibrations to shake the dust off. Lots of ideas being explored.
Clever. And what powers them while they're building these giant solar farms?
Good question. Initially, the 10 landed starships themselves. They'd act as the first power stations, using their onboard power generation to get a basic grid going while the robots deploy the solar arrays.
Okay, that makes sense.
Longer term, though, especially for heavy industry like ISRU or building big habitats, you'd almost certainly want to look at small, safe, nuclear fission reactors. They offer continuous, dense power regardless of sunlight or dust. It's a logical step, even if solar is the first focus for the robots.
Nuclear power on Mars.
Yeah.
That feels like a major milestone towards real settlement. And managing power for 10,000 bots? That sounds like its own complex dance.
It really is. Energy efficiency is critical. You'd program the robots with low-power modes, use regenerative braking when they move to recapture energy, optimize their motors.
Smart power saving.
Yeah, and you'd need charging solutions. Maybe centralized charging bays inside the starships, maybe even mobile charging robots that go out and talk up other bots working far away.
Like robotic fuel trucks.
Sort of. The whole thing would likely be run as a smart grid. Robots communicate their power levels. The system coordinates who charges when and where, all autonomously.
All right, they're powered, they're connected. But Mars, it's not exactly Earth-like, is it? What are the big environmental challenges they face right out of the gate?
Oh, it's a tough place. Temperature is a big one. The extremes are wild. Average is maybe minus 65 Celsius, but it swings hugely day to night.
Brr. That must be hard on materials and electronics.
Definitely. Stresses materials, affects batteries, lubricants. They'd need really sophisticated thermal management insulation, heaters, coolers, just to keep working properly.
And then there's the dust. We keep coming back to the dust.
Because it's everywhere. It's finer than talcum powder. It's abrasive. It gets statically charged, so it clings to everything.
Nasty stuff.
Yeah. It can wear down moving parts, block sensors, coat solar panels, clog up radiators. So really robust sealing is crucial. Advanced filters, and like we said, ways to clean themselves or get cleaned regularly. It's a constant battle.
And radiation, right? Mars doesn't have our magnetic field or thick atmosphere.
That's a huge one. Much higher levels of radiation from the sun and deep space hit the surface. That damages electronics over time, causes glitches, failures. It can also degrade materials.
So the robots need to be radiation hardened, like built tougher.
Exactly. Using specific design techniques and manufacturing processes, RHBD, RHBP, to make the electronics more resistant, maybe some extra shielding for the most critical parts. And the thin atmosphere itself doesn't stop micrometeoroids well, doesn't help much with getting rid of heat either.
So these bots aren't just exploring, they're basically surviving a constant environmental assault. How do they even start adapting?
Well, right after they land and link up, teams of robots, maybe specialized ones, would start detailed surveys, using LiDAR for 3D maps, cameras for detailed images, ground-penetrating radar to see what's underground.
Mapping the neighborhood?
Pretty much. Creating super detailed maps, finding hazards like big rocks or unstable slopes, checking how firm the ground is, maybe even sniffing out near-surface water ice. And while they're built tough, they'd also be constantly monitoring the environment, dust levels, temperature, radiation, and adjusting what they're doing. Maybe they hunker down behind a lander during a dust storm, or change their work schedule if it gets too cold or hot.
Smart adaptation.
And initial tasks would include things like clearing paths, maybe stabilizing a dodgy-looking slope, just making the immediate area safer to operate in.
It's like a massive automated survey and site prep operation. And these robots, they're not just dumb machines following orders, right? They have some serious capability.
Oh, absolutely. The vision is for highly advanced systems. Dexterity is key, being able to use tools, handle samples, operate equipment with precision.
Like human hands, almost.
Getting closer all the time. And their locomotion, likely bipedal or highly agile legged systems, lets them handle that rough Martian terrain, get to places wheels might struggle with.
And the brains behind the brawn. It's not just remote control.
No, definitely not. The AI on board is critical, especially integrating things like advanced vision language action models, VLA.
VLA. What's that allow them to do?
Basically, it lets the robot see its surroundings with cameras and sensors, understand complex instructions given in natural language either from humans or other AIs, and then translate that into physical actions. And crucially, do it with context.
So you could tell it, hey, go set up that seismometer over by that interesting rock formation, and it would figure it out.
That's the idea, yes. Figure out the best path, how to handle the instrument, where exactly to place it, maybe even troubleshoot if it runs into a small obstacle. It goes way beyond simple pre-programmed steps.
That's incredible. And would all 10,000 robots be identical?
Probably not. It makes more sense to have some specialization. You might have construction bots, ISRU bots focused on resource extraction, science specialists, maintenance bots, logistics haulers.
Different tools, different programming.
Exactly. It could be hardware differences, different tool attachments, or just different software and AI models optimized for certain tasks. And because of that communication delay we keep mentioning, they all need a high degree of autonomy. They have to interpret goals, learn from surprises, and work together effectively without constant hand-holding from Earth.
But they can't be perfect, right?
Mm-hmm.
Even super advanced robots must have limits.
Oh, for sure. Energy is a big one.
Yeah.
They'll need to recharge regularly. How long can they operate between charges? That's a key constraint.
Okay.
And while being versatile is great, a humanoid might be slower at, say, moving tons of dirt compared to a big, dedicated robotic bulldozer.
Not a tool for the job.
Exactly. And self-repair. They'd likely have some capability, maybe swapping out easy modules, but serious damage. Complex
Okay, so we've got this huge, capable, but not invincible robot army on Mars. What's the main goal in those early days and months? It's not just wandering around.
No, the main goal is ambitious. Start building a sustainable, expandable base, an outpost that can eventually support humans, and do it using local Martian resources ISRU as much as possible.
ISRU in situ resource utilization, using what's already there.
Precisely. And a huge focus would be construction using Martian regolith the soil and crushed rock as the primary building material.
Building stuff out of Mars dirt. Seriously, how?
Using advanced robotic 3D printing, techniques like contour crafting, where robots extrude a kind of Martian concrete, or maybe selective sintering, using lasers or microwaves to fuse regolith powder layer by layer.
Oh, like 3D printing houses, but on Mars with robots.
That's the concept. Using processed regolith mixed with binders, maybe brought from Earth initially, maybe eventually made on Mars too, to create strong, shielded structures.
What kind of structures are we talking about first?
A whole range of essentials. Pressurized habitats for future crews, shielded against radiation, labs for science and analyzing resources, maybe enclosed greenhouses to experiment with growing food, unpressurized shelters for storing equipment or doing maintenance, landing pads, roads or pathways between sites, dust barriers, and of course dedicated buildings for the ISRU processing itself.
A whole robotic construction site.
Absolutely. Coordinated teams of robots doing site prep, digging up regolith, running the 3D printers, assembling parts, doing quality checks. And they could work on multiple projects at once. The landed starships themselves would be part of it too, used as initial shelters, maybe linked together, maybe piled over with regolith for extra shielding.
It's mind-blowing. A city built by robots. And to keep it going, they need to live off the land, right? That ISRU becomes absolutely vital.
It's the cornerstone. Without large-scale ISRU, you're forever tied to hugely expensive supply runs from Earth. It's what makes long-term presence feasible.
So what are the top ISRU priorities for these bots?
Number one, almost certainly, is water. Finding and extracting water ice, probably from underground deposits. Robots need to prospect for it, dig it up, heat it to turn it into vapor, then capture and condense that vapor.
Water for drinking, breathing air, rocket fuel.
All of the above. It's critical. Second priority, oxygen. Getting oxygen from the Martian atmosphere. We know this works thanks to the MAHEX-E experiment on Perseverance.
Right, MAHEX made small amounts of oxygen.
Yeah, it proved the concept beautifully. So the robots would build much larger industrial-scale MAHEX-E-like systems to produce and store large quantities of breathable oxygen and oxygen for rocket fuel.
Okay, water and air. What else?
Construction materials, like we discussed. Processing that regolith into concrete, bricks, maybe even ceramics or basic metals eventually. And fourth, propellant production, using the hydrogen from water, ice, and carbon from the atmosphere to make methane fuel via the Sabatier process. That's key for return trips or fueling other vehicles on Mars.
So these robots are becoming miners, chemists, manufacturers,
Yeah.
building the industrial base.
Exactly. You'd see this integrated network develop. Water extraction plants feeding electrolysis units making hydrogen and oxygen. Atmospheric processors sucking in CO2 and churning out O2. Regolith processors making building materials, all run and maintained by robots.
And while all this building and mining is going on, you've got 10,000 potential scientists roaming around too, right? That's way more science capability than we've ever sent.
Oh, absolutely. It's a scientific revolution for Mars exploration. Even if many robots are busy building, a significant number, or specialized science bots, would be doing unprecedented levels of exploration.
What kind of science gear would they have?
A whole suite of advanced miniaturized instruments, spectrometers to analyze composition, leaves and XRF to zap rocks and see what they're made of, ground-penetrating radar to see underground, drills to get samples, high-res cameras, basically a walking geology lab.
But the really cool part is the AI, right? They're not just collecting data passively.
That's the game changer. AI-driven autonomous science. Give them a high-level goal like find signs of past water activity in this region. The AI plans the route, identifies promising rocks based on sensor readings, maybe decides to take a sample here, drilled there, do some initial analysis on board.
Right.
It could even potentially formulate simple hypotheses like, this data looks weird, maybe it's hydrothermal, and then decide to investigate that specific spot more closely, all without waiting for instructions from Earth.
So they're not just following recipes, they're actually doing science, making decisions.
That's the vision. They could work together to create incredibly detailed maps over huge areas, search for biosignatures, deploy networks of sensors to monitor Marsquakes or weather, track atmospheric changes, prospect for resources, just a vastly accelerated pace of discovery compared to one rover driving alone.
Okay, this is staggering. But managing 10,000 autonomous robots across Mars with that time delay, how do you even coordinate that symphony of steel without it becoming total chaos?
It's maybe the biggest management challenge ever conceived, right? You absolutely need a sophisticated, multi-layered approach. A hybrid coordination architecture, most likely.
Hybrid, meaning what?
Well, at the lowest level, you'd have localized swarms. Groups of robots working together closely on a specific task in one area, like building a habitat or surveying a crater. They'd talk directly to each other, coordinate their moves in near real time using that local Martian network.
Okay, local teams handling local jobs.
Right. Then above that, you'd need a higher level AI system, maybe distributed across the starships or specific command robots. This AI takes the big goals from Earth, build power infrastructure, search for water here, breaks them down into tasks for the different swarms, allocates robots and resources, and tracks the overall progress.
So local swarms managed by a central AI planner.
Something like that. And crucially, it has to be dynamic. If robots break down or a new priority comes up or they find something unexpected, the system has to adapt, reassign tasks on the fly. Humans on Earth would interact mainly with that top-level AI, giving it goals, checking summaries, stepping in only for major decisions or problems.
It's like managing a giant company where your middle managers are AI and you talk to them via really slow email.
Huh. That's not a bad analogy. And failures will happen. Robots operating 24/7 in that environment, things will break. How do you stop the whole thing grinding to a halt?
Yeah, resiliency is key.
Absolutely critical. Modularity is one answer. Building the robots from interchangeable parts. If a camera breaks, swap in a new one.
Okay.
You'd need dedicated repair shops, probably inside the starships or in purpose-built garages, staffed by specialized maintenance robots.
Robots fixing robots.
Exactly. And the robots themselves would need good self-diagnostics to spot problems early. Maybe even some basic self-repair capabilities, like swapping a component using onboard spares. Long-term, the dream is in situ manufacturing of spare parts, using Martian materials and 3D printing to make replacements right there.
Ultimate self-sufficiency. And that communication delay just forces this whole autonomous approach, doesn't it?
Completely. You have to operate on goal-based autonomy. Earth says, achieve X. The robots and their local AI figure out the how. It means they need powerful onboard processing to analyze their sensor data, filter it, make decisions, and only send back the important stuff, summaries, alerts, key findings, management by exception, basically.
So they're not constantly asking, Mother, may I? They're given a job and trusted to get it done. Looking ahead now, this huge robotic effort isn't just an end in itself. It's preparing for something bigger, right?
Yeah, that's the ultimate goal, yes. Preparing for humans. A massive part of the robot's long-term job description is building and testing everything humans will need to survive and thrive on Mars.
Like what specifically?
Robust habitats with reliable life support and radiation shielding. Labs kitted out for human scientists. Basic medical facilities. Food production systems like those greenhouses. Power grids. Communication networks. transportation systems. The robots would build it all and then rigorously test it, maybe even run simulations of human crews using the facilities to make sure everything is absolutely ready and safe before people arrive.
So the robots are the ultimate advance team, construction crew, and safety inspectors.
Exactly. You can think of the whole process in phases. Phase 1, land, deploy, get basic power and comms online. Phase 2, build core infrastructure, get ISRU really working. Phase 3, massive expansion, big science campaigns. Phase 4, sustain operations, final preparations, and rigorous testing for human arrival.
It's an incredible roadmap. But with so many moving parts, so much complexity, what about the risks? Things going wrong on a massive scale, cascading failures.
Systemic risk is a huge concern. A failure in one area, power grid, comms network, the key ISRU plant could potentially ripple outwards and cripple large parts of the operation.
And Mars itself can throw curveballs, like those planet-wide dust storms.
Exactly. Environmental hazards are a major source of systemic risk. Dust storms, extreme cold snaps, maybe unexpected geological activity. You need multiple layers of defense, redundancy everywhere, backup systems for everything critical, modularity so you can isolate a problem, maybe even diversity using different types of robots or software so a single bug doesn't take down the whole fleet, and smart autonomous systems that can detect faults, diagnose them, and try to recover automatically.
Planning for failure, essentially.
And you also have to worry about slow degradation, dust abrasion, radiation damage, things just wearing out over years. Constant monitoring and adaptive maintenance are crucial.
It feels like you almost have to anticipate the unanticipated. With 10,000 autonomous robots interacting, could they start doing things we didn't expect?
That's absolutely possible. Emergent behavior. Complex systems can sometimes develop collective patterns or actions that weren't explicitly programmed.
Would that be bad? Like robot uprisings?
Probably not sci-fi movie bad. More like maybe they develop an inefficient workflow or prioritize tasks in an unexpected way. The oversight AI would need to monitor for that kind of thing, manage it. But emergence can be good too. Maybe they discover a more efficient way to collaborate on construction.
And the potential for unexpected discoveries must be huge too.
Massively increased. With so many eyes and sensors constantly observing, the chances of spotting something truly novel, weird geology, unexpected atmospheric chemistry, maybe even subtle signs of life go way up. The AI needs a bit of programmed curiosity, you could say. The ability to recognize an anomaly, something that doesn't fit the pattern, and say, hey, that's weird, let's send a few science bots over there and check it out.
This whole vision, it's just breathtaking. It pushes so many boundaries. Think about it. That moment, the first humans actually land on Mars, step out and see. A world already humming with robotic activity.
Yeah.
A base already built. What's that first encounter even like? What new questions does that raise about us, about intelligent machines, about our place in the universe?
It would be profound, wouldn't it? Stepping onto another planet not as the absolute first pioneers breaking ground, but arriving at a place already prepared, already being worked by a vast non-human intelligence we created. It really shifts the paradigm.
This deep dive, wow, it feels like we've only just scratched the surface of how complex and fascinating this is. We really hope for you listening, this sparks more thought about the tech, the logistics, the ethics, all of it. What part of this robotic Mars plan really grabbed your curiosity? There's just so much to chew on as we imagine this future, a future maybe built first by robots, paving the way for the rest of us.